Okay. So my plan today is to tell you about rank, and then if I have time, to tell you about closure. So rank. Probably by now you have noticed that there's something similar to dimension in matroids, and I want to make this precise. So rank for matroids is going to generalize the idea that you already have for dimension in vector space. Okay. So let's say that you have a matroid M. Okay. So I'm going to define something called the rank function of M. It's going to assign a number to each subset of E. So it's a function from the collection of subsets of E to the natural numbers. It's defined like this. I know some folks disagree about what this means, natural numbers. And natural numbers for me means 0, 1, 2, and so on. For some people, 0 is not a natural number. For me, 0 is a natural number.
Wow.
The rank function is...
You think of 0 as natural?
0 is a pretty natural concept. Nowadays it is anyway. So the rank of a set, X is just going to be the size of the largest independent set in there. So it's the maximum size of an independent set, which is contained in X. Size of the largest independent set in X. And well, you guys thought about this in the previous homework, and you realized that actually all of the maximal independent sets inside X have the same size, because you proved that the restriction of X to the restriction of the simplicial complex I to the set X is pure. And therefore, every maximal independent set inside X has the same size. So this is the size of all the maximal independent sets in X, which we're just going to call bases of X. I think that's pretty natural. So size of all the bases of X. And we can say this because they all have the same size. You proved this. Okay? So this is the rank function.
Is that how you normally write it? Could you write like M restricted to X, or what's the notation that people...
Some people might write, you can write it like this, or sometimes if there are several matroids around, then you want to specify which one you're talking about, and you put subset, you put as a subscript the name of the matroid.
So X stands for any matroid, subset of E.
X is any subset of E. So maybe I didn't actually write this. Is this for each subset of the ground set? Let me just put out here the other notations that you'll see. So sometimes it's R sub M of X, and some people write rho also. I'm not going to use this, but if you see this rho, then probably it means the rank function. And I'm also going to define the rank of the matroid, which is just the biggest rank around. So definition, the rank of the matroid It's just a number, and it's just the rank of E. So you might write this R sub m or R of m. The point is that it's just the rank of the whole thing. Okay. So that's the definition of rank.
And that should equal the size of the bases.
And this is the size of the basis.
Okay.
Size of the basis.
Is the basis of E is the basis.
Right. Right. This is the rank function. And we're going to do the same thing that we did for when we translated from independent sets to bases or to circuits. What we want to do is now figure out what are the key properties of this rank function. So key properties of rank functions. Okay. So let me show you some key properties. The first one is pretty clear, which is that the rank of a set is between 0 and the size of the set. Okay. For any x. Proof, and this is pretty trivial. I mean, the rank is the size of something contained in X, and so at most it has size X. So the proof of this guy is trivial. The second property says that if you have X inside Y, then of course this guy should have bigger rank than this one. The proof of R2 is also pretty trivial, because all you have to do is say, consider a basis of X. It has R of X elements, and it's an independent set in Y. So there's not much to say there. And the third property is the one that is a little bit trickier, as usual. Yeah, we're used to this by now, that these two first ones are kind of trivial things, and then the third one is interesting. The third one tells you this, that if you look at the rank of X union Y plus the rank of X intersected with Y, then that is at most the rank of X plus the rank of Y for any X and Y inside E.
So, like in the initial definition of the matroid, it looks like at least these first two conditions make sense for any simplicial complex, and then is this third one kind of taking us into matroid land? Or
Right, so these two first properties are things that are going to happen in a natural notion of rank for a simplicial complex, if you can find one. This is really a more honest matroid property. Okay? And this is called submodularity. You might have seen that sometimes you have an equality here, and they call this modularity. And this is not an equality. It's less than an equality, so we call this the submodularity. Is there a question?
Akin to the dimension relationship in subspaces.
So, right. So what's the inspiration for this? I said rank is supposed to be similar to dimension. And you might remember a statement like this from linear algebra. In linear algebra, if U and V are vector spaces, are subspaces of some vector space, then we have something that is almost like this, but what's the difference? You guys remember? For vector spaces, it's actually an equality.
When you say U union V, you mean U plus V?
Sorry, I don't mean union, I mean U plus V. The subspace generated by U and V. So this is basically the inspiration for why you might guess that something like this holds. But if you try to prove this for matroids, you're going to see that it's not true. And this is what's true. And we'll talk about that in the forum. I want you to think about why this is not an equality, it's actually an inequality. So this is inspiration, but it's not a special case. As you can imagine, the proof of R3 is not trivial. But it's not too bad either, but we're going to do it. Okay. So let's prove that rank functions of matroids have the submodularity property. Okay, let's take X and Y. And I want to imagine them as subsets. Here's X, and here's Y. Okay. And now I'm going to do the following. Consider, so this guy right here is X union Y. Let's consider a basis of that guy. Okay. So let's say that some subset over here is a basis of X union Y. Intersect, sorry. So A is a basis of the intersection of X and Y. So we know how many elements there are in there. It's the rank of X intersection Y. Okay? Now, so this little guy is A. And now what I want you to notice is that A is an independent set inside X union Y. A is independent, and it is inside X union Y. And therefore, I can extend A to a basis of X union Y. So I extend it to a basis of X union Y. Okay. Let's call this basis B. Okay. So let's say that B looks like this. B is some subset of X union Y. Now, notice that A is already a basis for this guy, X intersection Y. So when I do this extension, I'm not going to pick any elements in here, because that would be dependent. So B is going to look like this. So note that the elements of B that are in X intersection Y are exactly the ones in A. I can't have anything else, because I would create a dependence. Okay. So this guy, this red thing, I'm going to call B. So B consists of these three pieces. And let me give names to the little pieces. So let me call this C and this D. Okay. And now let's just count. And I claim that if you count, you're done. What is the rank of X intersection Y? Well, it's the size of a basis of X intersection Y. A is a basis, so this rank is just the size of A. What is the rank of X union Y? Well, it's the size of a basis of X union Y. B is a basis of X union Y, so this is just the size of B, which is split into three pieces. Size of A plus size of C plus size of D. What can I say about the rank of x.
Greater than or equal to C?
It's so the rank of x is the size of the basis of x.
Yeah.
I don't necessarily have a basis of x at hand. But notice that A union C is independent. A union C is independent, and A union C is contained in x. So therefore, the rank of x is at least the size of A union C. Right? Which is A plus C. And I do the same argument for y. I don't necessarily have a basis of y at hand, but I can make exactly the same argument, and I get that the rank of y is at least A plus D. And I add up these two. I add up these two, and I get exactly what I want. R of x plus R of y is greater than or equal to 2 times A plus C plus D, which is exactly this. So I'm done. I'm sorry?
So that wasn't bad.
That wasn't bad.
It's actually very
You had to say something,
Yeah.
but it's pretty natural. Okay. So that's good. That means that rank functions actually do have these key properties that I'm talking about. And of course, you guys know what's next. Here we go to the same thing that I kept talking about with bases and with circuits and with all of this. That here you have these key properties of rank. And these properties are weak enough that you can prove them. They're easy enough that you can prove them. But now you want to prove that these are strong enough that you can recover the matroid from them. That these 3 properties are equivalent to defining a matroid. So that's the next thing, is that these key properties are, in fact, they are strong enough to recover the matroid.
You're saying you give me a set E, and you tell me the rank of each subset of E, and now I can put back together what that matroid had.
Exactly. So what Jameson is saying is exactly what I'm about to say. Theorem. Let's say that I give you a rank function. Let's say that I give you a function. So, okay, A is a fixed set. Then a function from the subsets to the naturals is a rank function, is the rank function of a matroid. If and only if it satisfies these 3 properties. What we might call the rank axioms are 1 up to R3. Okay. So this is, again, a different way of defining matroids. Okay. A little bit worried that this camera is not moving like it's supposed to. Okay, so to prove this theorem, there's 2 directions, right? The first direction is if you have a rank function, then it satisfies R1 to R3, and we did that. And for the other direction, what you would have to do is start with a rank function and tell me how to build a matroid. So given R satisfying the three axioms, how do you build the matroid? Okay. And the way you do this is, I mean, by now we know that there are several ways of recovering a matroid. If you can tell me what the independent sets are, then you're done. If you can tell me what the bases are, then you're done. If you can tell me what the circuits are, you're done. And any of these approaches is going to work. Let's go with independent sets. So how can you tell me if a set is independent? By looking at the rank. So you're going to define that a set is independent if and only if what?
Equals cardinality.
And only if the rank is the size of the set. So this defines a notion of independence, and now I have to check two things. The first thing that I need to check is that this actually does define a matroid. That's the first thing. But even when I do this, I'm not done yet, because I might be so unlucky that this matroid has some other rank function. So I have to check that this is the right rank function. Its rank function is R. How do you prove that it's a matroid? The same thing we always do, and I actually am not going to go through all the details, but basically you just have to check, does this definition of I satisfy axiom I1? Does it satisfy I2? Does it satisfy I3? And how do you check that it's the rank function? Well, you just prove that the definition of the rank function of this matroid matches with your rank that you started with. I'll tell you what the key. So let me just say I'm not doing the details, but I'll tell you what the key observation is. Let me go over there. So I'll omit the details. But I'll tell you what the key observation is. The key lemma is this: if let's say that you have two sets, and let's say that they have the property that the rank of, so if you take X and you add any element of Y, you don't change the rank. So what does this mean in vector land? Basically, this means that Y is in the span of X. Y is not increasing the dimension of your set. So the conclusion, as you might guess, is that if each individual Y is in the span of X, then all of Y is going to be in the span of X. Something that is clear and known to you for, linear independence. And it turns out to also be true for matroids in general. Okay.
That's it.
I'm sorry?
That's it. That's the.
This is the key observation. So when you try to carry out this proof,
Yeah.
once you know this, you'll see this is exactly what you need, and whenever you feel like you might have gotten stuck, this is what's going to help you. Okay. And I do encourage you to either try to prove this or read it in Oxley, and you'll see that the main thing that he uses is just this. Okay. And I actually want to prove this so that we get some practice on how you actually deal with these rank functions. I mean, here we saw one proof with rank functions. Now I want to show you a second proof with rank functions. So let's prove this lemma. The lemma says that it basically tells you that if you add y one at a time to x, and that doesn't change rank, then you can add them all at a time. And this is the typical kind of statement where you might think that induction is going to help you, because it's telling you to do things one at a time. We're going to do exactly that. We're going to induct on the size of y. So for example, if y is empty, then it couldn't be more trivial, right? The conclusion is that rank of x union empty is rank of x. If y is 1, then the hypothesis is the same as the conclusion, so there's nothing to say. Trivial. Okay? So now let's suppose that it's true for things of size, let's say n minus 1, and prove it for things of size n. Okay? So you take y which has size n, and your idea is that you want to add all of y to x. Well, if you're going to use your hypothesis, your induction hypothesis, then the only natural thing to do is to say, okay, well, y, let's first add n minus 1 of these things. And then add the last one. Arbitrarily. So let me just split y into a set of size n minus 1 and an element. Okay? So I know that rank of x union y is equal to rank of x for any y in big Y. In particular, this is going to hold for anything inside y prime. And to distinguish these things, let me call these little guys y prime.
You know the rank of x union y prime is the big Y prime is the rank of x, right?
Well, so what I'm saying is that because I know this, I can use the induction hypothesis to conclude that.
Oh.
So because I know this, I use the induction hypothesis, and that's why I know that I can add all of y prime and get the rank of x. Okay? But by the hypothesis, I also know that the rank of x union little y is the rank of x, where little y is now this specific element, little y. Okay? So now I know this, and I'm supposed to use these rank function axioms, and there's one that seems to do exactly what I want it to do, which is R3. So let's apply R3 to these two sets. So by R3, so my x and y are going to be these two guys, x union y prime and x union y. This is going to be greater than or equal to the rank of the union plus the rank of the intersection. The rank of the union is x union y prime union x union little y. The rank of the intersection is x union y prime intersection x union y. Okay? But x union y prime union x union little y, by definition, is just x union big Y. Plus, what's the intersection of x union y prime and x union y? Well, they have x in common, and y prime and little y are disjoint. So this is just the rank of x. And I already showed that the rank of x union y prime is rank of x. And I already showed that the rank of x union y is rank of x. And therefore, I cancel these guys, and I get that the rank of x union y is less than or equal to the rank of x.
That's say on the first line by R3 there. Yeah,
Here.
Almost where you just point to the right a little bit. Yeah, right there. What's that expression? The rank of x union y prime intersection?
Let me zoom in here. Here's that. It says rank of x union y prime intersected with x union y.
We need to know something like, I mean, it should be clear that the rank of x union y is greater than or equal to.
That's R2.
Right, I'm not done, because I want to show that these two are equal. And I showed one inequality, but fortunately the other inequality is a consequence of R2, which says that, well, this guy is x union y contains x, so by R2, its rank should be bigger than or equal to R of x. So I have one direction, I have the second direction, and I get my conclusion that I want.
So let me just think about the logic flow here. So this is a lemma that we want to use to prove that these axioms uniquely characterize rank functions of matroids. But we already showed the other direction that rank functions have these properties, which is why we were able to use it here, right?
Right. I mean, so this lemma. Maybe I should state more clearly the hypothesis of the lemma.
Yeah.
The lemma says let x and y be in E, and let R satisfy these conditions.
Okay.
That's my hypothesis. That's a very good point. Let R satisfy R1 up to R3.
So you're not calling.
So I'm not assuming yet that this is a lemma about matroids. So far, this is just a lemma about these rank functions that have this property. And by using this lemma, this is kind of the key lemma that allows you to show that actually, if you have this, then what you have in your hands is a matroid. Okay.
Because we're not using anything about matroids here.
Right, you see, I never used the word matroid in that board over there. I just used R2 and R3. And actually, I never used R1. So if you really want it, this is only a consequence of R2 and R3. Okay, so there's a lemma that is very useful to prove this. I also show it to you to give you an idea of how these rank proofs work. And I also give it to you because I'm going to need it in a second. So 3 birds in one stone. That's rank. And that tells you that a third way or a fourth way, or I don't know how many ways we have so far. This is the fourth way. So Our first way to think about matrices was through independent sets. Our second was through bases. Our third one was through circuits. And now we have a fourth way, which says a matroid is just a function that satisfies these conditions. And so you can think, what is another way of building matroids? Well, whenever I can manage to find a function in nature that satisfies these rank inequalities, I have a matroid. And sometimes this is how you prove that things are matroids. It's just by checking the rank conditions. OK. So that's rank, and that tells me that matroids have a notion of something that is like dimension, and it really behaves like dimension. The more that we practice with rank, we'll see that it really is a lot like dimension. And I should tell you, one of the homework problems is to give an alternative characterization of rank functions. That'll give you plenty of practice with the rank functions, and that'll also make it a little bit clearer to you why this is like dimension. So given that, I want to define closure for you now, which is another thing that we have in matroids. Another very useful tool. And here what you should be thinking of is that this is like a span. So in linear algebra, very often you make arguments about the span of this, the span of that. And the way of making that concrete for matroids is to talk about closure. Okay. So again, let's say that I have a matroid on E. So I'm going to define a closure operator. The closure operator is a function from subsets of E to subsets of E. So the closure operator of the matroid is given by so I need to tell you what the closure of a subset X is. You should be thinking that this is like span. Okay, so the closure is going to consist of, make sure that I use the same notation that I have here. So little x's. And the idea is that they are in the span of X. So what you want is basically that the little x doesn't increase the rank of big X. So the rank of big X union little x is the same as the rank of X.
So in linear algebra terms, you're just, if you have a linear matroid, you're just finding the vectors that were in your ground set to start with that lie in the span.
Exactly. So if your matroid is linear, and if you take a representation of the matroid, then what is the closure of three vectors? What you do is you take their span, and you see what other vectors of your collection are in that span. So this is closure. This is closure, and again, the next thing I want to do is key properties of closure. I'm sorry?
Can't use C's.
Right.
So what would you use?
CLs.
CL. I think by now you're also getting the hang of how these different notions, how you deal with a new notion in matroid theory. Well, a lot of the times what you want to do is you define it, and then you try to characterize it into things that let you recover the matroid. So Kim is right. People call these CL1, and so on. So closure should have several properties. Now, I think maybe some of you have already seen different notions of closure. So closure can be span, but maybe some of you have seen other notions of closure in mathematics. For example, algebraic closure. For example, topological closure. For example, generated subgroup. For example, convex hull, for those of you that took the polytopes course last semester. These are affine hull. These are all notions of closure, and the reason people call them closure is because there's three key properties that anything called closure should satisfy. So the first key property that a closure should satisfy is a pretty trivial one, which is that the closure better contain the thing that it's in. The closure of X should contain X. And the idea is that you're taking X and closing it. If you started with X, this property should be trivial. The second property that closure has is that, so this is for all subsets. Whenever we have a new axiom system for matroids, one of them deals with what happens when you have two nested things. What if X is in between Y? Well, probably you can guess that if X is a subset of Y, then if you close X, it's going to be a subset of the closure of Y.
In E, does your E in this sense kind of represent the whole big space, or just the ground?
E is the whole big space, which you might think of as the big group. If you're talking about generating subgroups, you can think of as the topological space you're working with if you're talking about closure.
Yeah.
This is kind of a discrete version of that. It is a discrete version of all of that. There's a third property, which is that there's things called closed. And when you close something that's closed, you don't do anything to it. So for all X, if you close X, and then you close that, then the second closure didn't do anything.
So you define something.
It was closed already.
Closed if its closure is itself.
Right. Right, and this is something that closures always satisfy, that the closure of the closure is the closure. And I should tell you this, I mean, this isn't just an observation about, this really comes from the point of view of category theory, that these really are the things that deserve to be called abstract closure operators.
It's like the idea of an equivalence relationship or something like that. Like these span.
Right, so that's a good way to think about it, that the notion of a closure operator is a little bit similar to the notion of equivalence relation. You don't just call something an equivalence relation. An equivalence relation has certain properties that every equivalence relation in mathematics has. And if you want to call something a closure in mathematics, then it better satisfy these three things. So it's good that our notion of closure satisfies them. Now, maybe the thing that is uninteresting so far is that if this is true of any closure, then what makes it different? Being that we're living in matroids, and so actually we needed a fourth axiom, which is really the so burn your chip. What are we going to do now? And this is going to be really the more matroid. I mean the axiom that separates matroids from other closures, and it says this: if you take a big X and a little x, now you're going to assume that, so basically for every element y that is not in the closure of X. But it is in the closure of X union X. So you had an element that was not in the closure of X, but now if you add little x, then Y appears in the closure.
Oh.
Then you can exchange X and Y. Then you can exchange X and Y and say that actually X is also in the closure of
Is that equivalent
X
to saying
union little y.
little y is in the closure of little x, or not? That's not quite right.
This is not equivalent to saying that Y is in the closure of little x. So these two things do not, I mean, because think about it. What this means is Y is not in the span of X. I mean, if we think about it in terms of vectors, it means Y is not a linear combination of X, but it is a linear combination of X and little x. So what that means is that you have an equation that involves Y, it involves little x, and it involves maybe things in X. And therefore, you have an equation that involves little x, involves little y, and involves all of X. So again, this is easy for linear independence, and we want to show that it's true for any matrix. So this is called the exchange axiom because it lets you exchange from X to Y. It's pretty suggestive that
So this
is the
additional axiom uniquely characterizes closure for matroid.
right. Exchange axiom. So the closure exchange axiom. And so your guess is correct, of course, that this exactly characterizes matroids. Again, so this is another way of thinking about matroids. So we just state the theorem. Let E be a finite set. Then a relation, a function. We call it an operation. Did I call this closure operator or operation? Operator. There's nothing to that word. It's just I want to be consistent. So an operator from 2 to the E, from the subsets of E to the subsets of E is the closure operator of a matroid if and only if closure satisfies these axioms. Okay. So this is the theorem. And a restatement of the theorem is that matroids are essentially the same thing as closures that satisfy the exchange axiom. Are equivalent to, are basically closure relations.
I've heard people say closure spaces before.
Closure spaces, I don't know what the formal definition of closure space is, but probably it fits in here just fine. Matroids are closure operators satisfying the exchange axiom. And so the good news about this is that now we have a whole new tool because people are used to dealing with closures in all fields of mathematics. And we can just borrow everything that they've done and use it here, which is what we're going to do. So next time what I'm going to do is I mean, in this case, it's not so clear that these axioms hold for matroids. So I'm going to prove these to you. And I'm going to give you an indication of how to prove the theorem next time.
I was to teach 711 this week, and we're learning about Banach spaces. So I was thinking all night last night, the Banach space over an algebraically closed field is kind of like the most closed thing you could ever hope for. Like anything that you're going to be able to construct from that thing is going to be in any root of any polynomial, any limit of any. So I was really thinking about that idea of things being completely closed. I mean, I guess you need to add a point at infinity or something.
What?
Yes, just a Banach space is
you don't have all your
logically closed and algebraically closed.
You don't have your stacks. They're getting tested.
So sit here and study.
Good. That's what I'm doing Friday.
Yeah, Monday I don't know.
You don't broadcast your calculus lectures?
Yeah, I watched the
Huh?
Matroids, the lectures.
You are? It just kept going after? That'd be funny.
Be glad that at least we're not doing this.
Just taking cross products, that's all you're doing.
Really?
So you said, no.
I was like,
Our brother's here today.
Oh yeah? On campus?
Are you teaching this class or are you in this class? This is one before.
I'm teaching an expert on the charts. No,
I just
I'm
erased
just
the board
in it. He's my student aide.
This is like for your graduate school?
She's writing on the board.
What math is this?
That's really short.
Oh my god. That shit was terrible.
Actually, I gotta call my girl right now because I'm feeling the wrong thing.
You guys have your blue books, right?
Yeah.